All right, today we're going to be looking at section 4.3. What does the derivative tell us? I'm going to give a general overview and talk about some of the terms. So first, we have increasing and decreasing functions. You're given the mathematical definition. So suppose a function, and usually we denote a function with the letter f. It could be like y equals 2x plus 5, anything like that, a quadratic, some kind of function. On some interval, it could be from 0 to 10, it could be 1 to 5. We just use arbitrary letters. We say from x1 to x2, two different x values where one is greater than the other. F is increasing. If the function is increasing on the interval, the f2, which is corresponding to the y value. So the y value above the second x point is going to be greater than the y value above x1, the first x point. So as you go from left to right, the function is going to be going higher. If the function is decreasing, it's going to be just the opposite. F2 is going to be less than F1. So the y value here is going to be greater than the y value here, but it just says it in the other way. It says this y value is going to be smaller than this one. So left to right is going up, it's increasing. Left to right going down is decreasing. But this is the mathematical way that you interpret that. All right, so here we're talking about the mean value theorem, some of the other things we're going to be looking at. Now, when we do the derivative is the slope. And so what we want you to know is that the slope of the tangent line to the curve is also doing the same thing that the function is doing. So when you take the derivative and you do the tangent line at a point, you can see this red line is still going up left to right. It's increasing on both of them. Same thing here. These tangent lines have a negative slope. So when you take the derivative, that slope is also decreasing. This is going to tell us how to test for increasing and decreasing intervals. We're going to take f be a continuous function, and it has to be differentiable at all the interior points. Then if the derivative is greater than 0, then we know the original function is increasing. If the derivative is less than 0, we know that it will be decreasing. So this kind of goes through the proof and then gives us an example in sketching. We will do the derivative, set it equal to 0, find those maximum and minimum values, and then we will test numbers in between to see if they're positive or negative. We don't really care about the actual value of the number. We're just looking at the sign to see if it's positive or negative. And I'll show you a little bit more of this when we work them in my math lab. Here's a function that would be problematic. It's a corner point, so this would not be differentiable. This would fail to satisfy the condition that the function needs to be continuous and differentiable. You can kind of see some of those 0 tangent line points. So it's like a minimum point, a local minimum, or maximum inflection point, which we'll kind of talk about some of those. So here's some examples that they're giving you. This image kind of goes with this example, and what we're seeing is the original black line. This is a cubic function. This is the function we're looking at, f. When you take the derivative, it is giving you the positive or negative sign of the function. So this black line is increasing, increasing, increasing until it gets to this dotted line right here. It shows you where there's a change. As you know, this red line in position is above the x-axis, indicating that it's positive. So when I plug in a value to this 6x squared, I'm going to get a positive, 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 positive value until I hit this point, and then it goes below the line and goes negative. That's where the direction of this line changes from going up to going down. So when it starts going down, it's decreasing. This is a negative value. All right, and then it changes to increasing again, and then it goes above the axis for positive. So that's kind of something that you'll visualize. Like you can kind of somewhat sketch a derivative function by knowing increasing and decreasing intervals. This talks about identifying local minimum and maximum. Here's the first derivative test. It just tells you assume f is continuous on the interval that contains a critical point c, and we're going to assume it's differentiable on an interval containing c except perhaps at c. And it says if f prime changes sign from positive to negative as x increases through c, f has a maximum. So it's going positive and then starts going negative. That means you got a hilltop. It's going to be a maximum. If it changes sign from negative, it was going negative slope and then goes to increasing through c, it's a minimum. If f is positive, both sides are near c, it has no local extreme value at c. And then here's some examples using those. Gives you the proof. Those will be some good reading. Here's a visual example of what that process looks like. And then we're going to look at some absolute extreme values on any interval. It says one local extreme implies absolute extreme. So we have some continuous function on some interval if it contains exactly one local extreme at c. If a local maximum occurs at c, then f of c is the absolute maximum on the interval. They're going to give you a little visual. It could be any interval, shortened or expanded, depending on what we're looking at. And then it also, if we have a minimum at c, then it's going to be an absolute minimum on that interval. And then we give you some examples, some visuals of seeing inflections. This is the next thing we're going to talk about, inflection and concavity. These are also in your notes online in the cheat sheets. We're going to let f be a differentiable function on an open interval I. If the first derivative is increasing on I, then f is concave up. If the first derivative is decreasing, then the original function is concave down. And then if f is continuous at c, f changes concavity at c from up to down or vice versa, then it's an inflection point. So we can see that this is going concave up, this is concave down, up and down, and then the change in concavity through this line could be considered an inflection point, changing from concave up to concave down. But we'll see some examples of those as well. Here's how we test for concavity. We're going to look at the second derivative. So if the second derivative is greater than 0, it is concave up. If the second derivative is less than 0, concave down. If c is a point of the interval where the second derivative changes sign at c from positive to negative or vice versa, f has an inflection point at c. All right, so just saying the same thing. So here we go from concave down to concave up. You got an inflection point here. This is going concave up and it's still concave up, so not an inflection point. Concave up to concave down, got this inflection point here. And then we have a corner point, so that's not, we can't take the derivative, not differentiable is the term, and so that's not an inflection point. All right, then they give you some examples, some visuals, and we'll do some of these when we flip over to the problem. Here is just a little bit more information on the second derivative test. Another way to locate local extrema. So you can also look at the second derivative. If it is greater than 0, we have a minimum. If it is less than 0, we have a maximum. And then f of c equals 0, we are inconclusive. And then you can kind of get some visuals of that as well. Some examples that would be good to practice. Here are some of the properties, just a recap of things to look at. And I think with that, we're going to jump into some of the practice problems.